Now, coming to the Hamiltonian version of this, corresponding to generators of symmetries, there exist dynamical variables constructed from canonical variables P and Q, such that the symmetries are, and we call it implemented on the phase space. So, effectively the phase space of canonical mechanics becomes the carrier space of the symmetries. This is the main message of classical story of symmetries and physics, and there is a book by Sudarshan and Mukunda which is all about that. So, in symbols, for example, let us work through examples because that is the best. Delta R equal to delta phi cross R. Okay. This is small rotation, infinitesimal rotation. So, I have been meaning to tell this for quite some time, so let me spend a few minutes now to do it here. Note that the cross product is actually rank 2 antisymmetric tensor. So, when we say delta phi cross R, say x component, it is supposed to be delta phi y times z minus delta phi z minus y times y component. Right. So, there are two small rotation angles, one which is y axis delta phi, z axis delta phi z. So, there are two parameters, but that is what it is. Okay. So, actually what we do is we map, due to accident of 3 dimensions, we have available the Levi-Civita tensor with 3 indices. In in any number of dimensions you can write the corresponding epsilon tensor, but it will have that many indices. It is the completely antisymmetric tensor in that many number of dimensions. Its geometric interpretation is that it is the volume element. If you write epsilon ijk dxi, dxj, dxk, that amounts to writing the volume element of the 3-dimensional. It is same as the triple product. So it gives the volume because it says A dot B cross C So when I do B cross C, I get something here. But then there is A here, and if I do A dot B cross C, I basically get the volume of this parallelepiped. B cross C, sorry, B cross C will produce BC sine of the angle between them. So that will anyway, so this basic, and that is exactly what this will be same as epsilon ijk ai bj ck. But now the point is that using the epsilon, we can convert any antisymmetric tensor into a vector, a pseudo vector. Okay. So just to count, note that in 3 dimensions we will have exactly 3 components to the antisymmetric tensor, because the tensor is a 3 by 3 matrix, but it is antisymmetric, so it has no diagonal elements, and if you count the upper diagonal, it is 3 elements, remaining 2 and 1. So thus we can map an antisymmetric tensor with 3 independent components. And it gets mapped into 3 vector like looking components, and we put a factor half because it will double count. J1 will contain J23 and then minus J32, which because of the antisymmetry again becomes J23, so we get it twice, so we put a factor half. And we can check that if R transforms as then L or J, we have called it here J will transform exactly according to the R matrix. After you put the epsilons and so on, you get exactly that this transforms like this. So hence the name pseudo vector. Because it will be seen to transform according to R, but if you flip the coordinates, then because both R and P will change sign, J will not change sign. So it is called a pseudo vector. So coming back, corresponding to the 3 quantities, that the Poisson bracket of J. So coming back to this, so it covers also. So if I have a geometric symmetry that R can be shifted to delta R, shifted by delta R using some parameters delta phi, then the corresponding J that I construct will be such that its Poisson bracket. So Ji on Rk or Ji on Rj, sorry for too many J's, Poisson bracket will exactly reproduce delta R delta Ri and times whatever the effect of this is going to be. So probably a delta Ij. It will rotate on, so times delta J, okay, that's enough, right. Okay. So if I take the, so here I have the, these are the parameters of the transformation. I hope this is, it's okay, no, you are keeping track of this. So I have the geometric transformation is delta R goes to, is related to R, proportional to R with parameters delta phi. Now I take the corresponding conserved quantity, which is the angular momentum, and supply the same parameters. If I now act with this on R, it will reproduce exactly delta Rj equal to delta phi cross R, jth component. Okay. That is the statement of it being implemented in the canonical sense. So we can check this. Let us try out one thing. So suppose I take, but it's much easier to do in quantum mechanics because you only have to compute commutators. But in any case, here also it is okay. So suppose we take Jz on, let us say, x. I keep writing this because the curly brackets have begun to have connotations of spinor anti-commutator in quantum mechanics. So just to remind ourselves that we are with the classical canonical mechanics, we write this. So this is equal to Jz is equal to ypx minus xpy commutator Poisson bracket x. So do we have it? So we are trying to check this action of Jz on x. So we put the generator Jz. Now we use just the properties of the Poisson bracket because the bracket has essentially linearity and distributivity. So it is same as from the first term, it would be y px x then plus y x px plus so minus x py x and then minus x x py, but all of these will vanish because yx Poisson bracket x with a canonical variable not conjugate to it, all of these are 0. and Pxx is minus 1. So, this gives minus y. X Px is plus 1. So, Pxx is it is an antisymmetric operation. So, it exactly gives minus y. So, this is exactly what you expect from the effect of a k cap times delta phi cross r. Okay. I kept z component. So, this is the way it gets implemented in this particular way. Well, I do not need to write this. So, it is times j cap, it will come out proportional to j cap, which is y. Now, in general, therefore, and let us list these with some other labels. So, it is some internal label. These are not the canonical labels. Here they get mixed up because they are themselves space-time symmetries, but they do not have to be space-time symmetries. So, this is the core statement of what this is in canonical language, where G itself is constructed out of the canonical variables. So, any symmetry operation is implemented like this, and the G's all commute with the Hamiltonian. Yeah, so I think basically once you have this zx, because the internal index I became same as an external index. So, this becomes a zx, which is why we got y, or that is why the j cap by j cap I mean the zx component. Okay. So, finally we come to symmetries in quantum mechanics. Fortunately, because of the great observation of Dirac that the quantum mechanics amounts to carrying over Poisson brackets to commutators. Sorry. So, commutator goes to I h cross times this, and that becomes equal to the quantum commutator, i.e. the corresponding Poisson bracket. Okay. And this is in general true for any variables, but the strategy is strategy cum prescription of quantum mechanics. Express all dynamical variables in terms of the canonical ones. This statement itself can be a stumbling block sometimes in quantum mechanics, because you may encounter new observables for which there is no canonical description. That is why it is a prescription. And a prime example of this is spin, intrinsic spin. For which there is no classical analog. Okay. And similarly, because of this fact, when we go to fermions, the fermionic quantization rules are completely out of the charts. Luckily, it looks like just a clever change. Instead of commutators, you do anti-commutators. But why you have to do this is not clear. We learnt it the hard way, and it kind of extended the analogy. Okay. The anti-commutators ensure Pauli exclusion principle and everything. But it is something auxiliary that didn't come out of the simple prescription. But the core strategy, to the extent this is possible, we can bosonic or fermionic. We can construct Gi out of the canonical variables which may be either bosonic or fermionic. And the general statement that operators G exist so that now Gi on your variables Qi, now a commutator, equal to classical answer. Okay. It reproduce on Q. Wigner also, so the same thing that we wrote about J acting on this, now using commutators, but because of the analogy with Poisson bracket, the calculation exactly remains the same, and then you get the same answer. But the exception is that more precisely either unitary or anti-unitary operators exist in QM which can be constructed out of its canonical variables. So that above implementation works. Implementation works through the quantum brackets. So the quantum variables now become the carrier space of the quantum symmetries. We need not write that. There are lot of intricacies that arise when we go further with this, but for the time being I will leave it at this, that it works like this in quantum mechanics almost exactly the same way it works for the classical system, provided you keep track of the canonical variables. Every once in a while you will not be able to construct a quantity out of canonical variables, then you supplement it by whatever new is there, again determine what their Poisson basic brackets have to be, but then again anything else you construct out of it you can continue. The last comments I want to make is that there are symmetry alone determines the classical wave equation. Okay. But let us just go to the issue of gauge invariance and dynamical symmetry. So the story begins by observing that Lorentz force can be obtained in canonical framework from H equal to 1 over 2m P minus Q over C times A. So if you do this, then it will automatically generate the Lorentz force. You shift, in other words, you shift P by A. So this is given in Goldstein's chapter 1. Okay. Well, Goldstein chapter 1 gives the Lagrangian version. but you will see it's same thing, it's q dot minus q over c a, then you find the canonical quantities, they become like this. So in quantum mechanics, expect that minus I h cross gradient, which is what stands for p, which is same as shifting p. Now if you write this for a particle, so this form absorbs the gauge invariance of electromagnetism. So the gauge invariance of electromagnetism is E is equal to minus gradient A0, minus gradient A0 and minus d by dt 1 over c d by dt of vector potential A, and B is equal to curl of A. So E equal to minus grad phi is of course electrostatic statement. In electrodynamics you need to add the d by dt term to take care of the Ampere's law correctly. Once you introduce B equal, this is always possible because div B equal to 0, and once you do this you can then do this. Now this has a strange local invariance. Term given by Hermann Weyl, which is that if I change A to old A minus the gradient of some lambda of x and t, and change A0 plus the time derivative of then we can make these two get compensated here. Okay, so 1 over c d by dt of grad lambda can be compensated by minus grad of, so we need a 1 over c here, 1 over c d by dt of lambda. Okay. So E changes by this, and then therefore we get 0. So E and B don't change. This is why Dirac called Weyl a genius he fears. So there is a simpler way of looking at it. B is curl of A. It is obvious that A is going to remain ambiguous, because to A I can add gradient of any scalar, and because curl of a grad is always 0, that gradient can always be added. So that much is somewhat simpler. But that there is this combined gauge invariance where you also shift E by time derivative of A and shift the scalar potential by this, makes for a larger gauge invariance where there is a space time dependent degree of freedom. So this is essentially an infinite dimensional freedom available. If you count in terms of group theory freedoms, it's a huge amount of degree of freedom, but the plot gets thicker now, because when you now combine this with this particular form of how electromagnetism couples to a point charge, you can then modulate the phase of. So let us look at this. So now note minus I h cross grad minus q over c a prime. Suppose I have this acting on psi prime. So that would become equal to so I am looking for what should be psi prime, and let us say it is going to be u of x t psi. When I shift the a, q over c into a minus gradient lambda u of x t psi, that is what it will become. So this we do not know what u to put there. If I do this gauge transformation on A fields, what should I do to psi prime so that my Hamiltonian does not change? Remember that the physical electromagnetism is not changing when I change the A like this. So I have to somehow compensate it by changing, identify what change in psi to do this. And the answer is that this gradient u times psi and then minus u times minus I h cross grad psi, right, just letting this term act on this product, this and this, and times minus q over c a u psi and plus q over c grad lambda times u psi. All of this has to remain the same. Now it has to look like the older version of the Lagrangian. This works provided, so I gather these two things together because they are my old form. They are equal to u times minus I h cross grad psi, and these are can be taken out. U is some overall factor. Here there is no derivative involved, so I can take this u out and it remains inside minus q over c a psi, right. But then these two I should get them to cancel. So there is a plus sign here. I can get them to cancel provided require that there was gradient u, right, this was gradient u. I h cross grad acting on u first and then grad acting on psi. So this means that minus I h cross grad u should be equal to or plus this equal to q over c, taking this on the other side, q over c grad lambda times u. Okay. This can be achieved if you notice that u should be equal to e raised to, so you can put this u below here and think of this as log. So then it becomes equal to e raised to minus I h cross q over c times lambda. We will solve this. I take times, so u equal to this will solve this differential equation. So, is plus sign or minus sign? Plus. No, so we made a mistake. So we need to do a little board work. So du, very roughly speaking, du over u equal to minus I q over h cross c, right? Times d lambda. So ln u equal to this times lambda. So u equal to e raised to minus I q over h cross c times lambda. Good. So this was correct, except that the sign was, and placing of h cross was not correct. So I pick a u of t psi prime of x t equal to x So if I play this game of shifting the electromagnetic potentials by gradients of lambda, I can compensate it by shifting the phase of psi in a space-time dependent way. This is the big thing. So note that, so this is where we will end, forms the group U1, that is unitary matrices of size 1 by 1 size. But now here we find electromagnetism has a space-time dependent. This we call local gauge invariance. The point of local gauge invariance is that it does not give us any new conserved quantities. It is a symmetry, gives no new conserved quantities. There is only still the electronic charge, but determines the form of the Hamiltonian. Oh, great. You have to always construct a quantity in which the factor u drops out. You cannot construct it in any other way. So it fixes the interaction of the electron with the electromagnetic field. And therefore called dynamical symmetry. Okay. And the greatest news of 20th century is that the weak force, strong force all follow the same rule. Or perhaps of all times, If there are only 4 forces of nature, we have finished the story now. But with groups, SU3 color, so then there are 8 photons, there are 8 gauge potentials cross so called SU2 left cross a U1y. So electromagnetism comes out of linear combination of the two. The U1 of electromagnetism is linear combination of those two, but this SU2 acts on the doublet of electron and neutrino, and SU3 acts on the quarks, triplet of quarks. And this acts on left-handed neutrino and the left part of electron, left projection of electron. It does not affect right projection of the electron. So, it is slightly strange theory, but this is how it is. Okay. But the dynamics is completely fixed by these, and with 3 couplings, E, you can say G weak and G strong. So, just those 3 numbers fix everything that you have in terms of interactions. All the embarrassment comes in the masses, because you do not know where the masses come from, but that is where the Higgs mechanism comes and so on. But the core of the dynamics of the theory is fixed by this. Okay, so, that is the end of, this is the end of the course.